Determination of molecular weight of macromolecule by light scattering method. As you know, according to Beer-Lambert's law, the intensity of light decreases when it passes through pure substance or solution. Increase in thickness of material as well as increase in concentration of solution, more light energy is absorbed and hence intensity of transmitted light decreases. Whereas due to bigger size of macromolecule in solution, turbidity is produced. Due to turbidity, light is scattered when passed through macromolecule solution. Sometimes the intensity or direct transmitted light is very small. In such a cases, the light is received at right angle, that is 90°. This fraction of incident light scattered per unit length of solution through which it passes is called turbidity, and it is given by equation IT is equal to I0 into e raised to power minus tau L, where I0 is intensity of incident light, IT is intensity of transmitted light, whereas L, as you know, it is length of solution. In case of solution of most of protein and high polymer, turbidity is very small and it is determined by measuring the intensity of light scattered at 90° to the beam. Turbidity is more when concentration of solution is more, as well as more molecular weight. So turbidity of solution is related with molecular weight of the macromolecule. The equation is given in 1944 as Sc upon tau is equal to 1 upon m plus twice v. As you know, this equation is equation of straight line, that is y is equal to mx plus c. So on y-axis, if we take Sc upon tau, on x-axis concentration, then what do you get? A straight line is obtained. The intercept of straight line gives value of molecular weight, that is 1 by m, whereas slope of line will be b. Thus you can write limit c tends to 0, Sc upon tau is equal to 1 by m, where b it is nothing but second virial constant and h is a constant which can be calculated by using expression h is equal to 32 pi cube eta 0 square in bracket del eta upon del c whole square divided by thrice n0 lambda raised to power 4, where eta 0 is refractive index of solution. Del eta by del c is nothing but variation of refractive index with concentration. N0 is a Avogadro's number and lambda is a wavelength of incident light. The value of N0 and del eta by del c can be determined by refractometer and differential refractometer respectively. Thus, once the value of h and t are determined, it is possible to plot a graph between Sc upon tau versus concentration C, and the curve is straight line which is extrapolated to 0 concentration. The intercept gives value of 1 by m, where m is nothing but what? Molecular weight of macromolecule. Now there are various limitations of this method. First one is that this method gives incorrect result above molecular weight 10 lakh. Second one is that dust also scattered light, thus dust may cause problem and gives incorrect result. Next method for determination of average molecular weight of a macromolecule is osmotic pressure method. It is also called as membrane osmometry. It is widely used technique for determination of number average molecular weight of a polymer. It is based on phenomena of osmosis. Friends, as you know, a membrane is that which allows only one species to pass through it but not the other. If a pure solvent is separated from solution by a semi-permeable membrane, then due to difference in concentration between solvent and solution, the solvent molecule diffuse into the solution through membrane. The flow of solvent can be stopped by applying pressure to the solution. Thus, osmotic pressure is defined as the pressure that must be applied to solution so as to totally prevent the flow of solvent through the semi-permeable membrane into the solution. The theory of osmotic pressure is also applied to solution of polymer. As you know, ordinary solution obeys one Top's equation, that is P is equal to CRT upon M. You know, up to concentration of about 1%, serious deviation occur in polymer solution. Since 1% polymer solution is not a dilute due to high molecular weight, thus deviation from ideality due to presence of large range of macromolecule. Macromolecule gives strongly non-ideal solution. Taking into account deviation from ideality and applying thermodynamics, in 1945, Macmillan and Mayer modified the Van 't Hoff equation. The equation is P is equal to RT upon M into C plus BC square plus DC cube and so on. So by taking C common and shifting towards left hand side, we get equation P by C is equal to RT upon Mn plus BC plus DC square plus and so on. For dilute macromolecule solution, C is small. Therefore, DC square and onward terms are neglected. Thus, equation becomes P by C is equal to RT upon Mn plus BC. Now, this equation is similar to equation of straight line, that is y is equal to mx plus c. That means on y-axis, if we take P by C, whereas on x-axis we take C, then a straight line is obtained with intercept RT upon Mn and slope B. This graph is shown where C is concentration in mass per unit volume. Now, how to measure osmotic pressure? So, for that purpose, high-speed membrane osmometer is used. High-speed membrane osmometer consists of two cells separated by membrane. There is solvent in upper cell and solution in lower cell. This arrangement is connected to reservoir filled with same solution of macromolecule through a capillary tube. There is an air bubble in capillary and its position or moment can be detected by photocell. Photocell connects to a servometer. When the osmosis takes place, the solvent enters into solution, which can be checked by upward or downward position of solution in reservoir using servo mechanism. The height of solution in reservoir carried upward or downward will be the pressure required, which is nothing but a osmotic pressure. And thus, by measuring osmotic pressure for different concentration, and if a graph is plotted between P by C, that is osmotic pressure upon C versus concentration, then what we get is a straight line, the intercept of which gives us the number average molecular weight. The advantage of this method is quicker determination of molecular weight of macromolecule, that is within 5 to 7 minutes. By this method, the molecular weight ranging from 30,000 to 30,000 lakhs can be measured, and limitation is non-availability of ideal membrane. Thank you for watching this video.